bond. Now, looking at the polar covalent bonds just a little bit more, we do know that each side of that bond will have a tendency to be a little tiny bit negative and a little tiny bit positive. And what we get is what's called a dipole, or a bond that has two different polar sides, a positive and a negative. And that amount of difference, how big the negative and how big the positive is, can be measured. And it's measured in a value called a dipole moment. Okay. It is calculated, okay, mathematically using a value that has some charge associated with it. We'll come back to that mathematically at the end of this chapter, but it's measured with a new unit of charge. Okay? What I really want you to be able to do at this moment in time is not mathematically calculate anything, but I want you to understand what it really means. And so if I take a look at these four different bonds, one between hydrogen and fluorine, one between hydrogen and chlorine, one between hydrogen and bromine, and one between hydrogen and iodine. Okay, what we're doing is hydrogen has the exact same electronegativity in all of those, but what changes is what atom is bound to, and it changes their electronegativity difference. And so if you can take a look, fluorine was the most electronegative bond on the periodic table, and so hydrogen and fluorine, electronegativity difference is greatest, and so the value of its dipole, or its unbalancedness, we can say, is the greatest. And you can see that one side becomes blue, one side becomes red, positive, this side becomes negative. And as we go down, the differences become less, so the amount of unbalance, the dipole moment, becomes less. Now, this will influence the bonds and the behavior of the atoms when they react in the real world. Okay, so we're never going to get away from electronegativity. It will be used to justify why atoms react from now until organic chemistry and through biochemistry and all the way through physical chemistry. So this understanding of electronegativity difference and polarity is important. So, if I take a look at these three bonds, boron to chlorine, carbon to chlorine, phosphorus to fluorine, and phosphorus to chlorine, okay, which atom has the partial negative charge? Okay, in these cases, if I look at boron and chlorine, I'm going to compare two elements, boron and chlorine. The one that has the greatest electronegativity, and electronegativity goes this direction and that direction. And so chlorine is below boron, but it is much more much more to the right. And so chlorine is much more electronegative. And so I would indicate this being the partial negative on this side, the partial positive on that side. You may see written this way, the charge is headed towards, the negative charge is headed towards the chlorine, the positive charge is headed towards the boron. Chlorine and carbon, chlorine and carbon, again, would have a bond that would look like this. Phosphorus and fluorine, well, here's phosphorus, and we know fluorine is the most electronegative, so the bond would look like that. And phosphorus and chlorine, we would have a bond where the phosphorus is partially positive, the chlorine is partially negative. Okay. The last item in terms of bonding we've looked at covalent as one model. We've looked at ionic as the other model. We've looked at polar covalent that's kind of in the mix. But the major third bonding is called metallic. Now, metallic happens when metals are bound to each other. And so in this case, if you had a block of sodium sitting right there, what it would represent is a sodium atom and a sodium atom and a sodium atom all next to each other. And what they do is they line up in a wonderfully grid-like pattern. And they create what's called a lattice. And so each sodium is next to each sodium. Now, one thing about metals is they tend to have very little ionization energies. That means the electrons are not attracted to the nucleus very well. And so what happens is the electrons for each of these sodiums, when it's bound to sodiums, actually love to flow between all the metals. And so the metal centers are all next to each other, and they're not really sharing the electrons in a typical sense. They are sharing all of the electrons, and the electrons are so easy and readily to move. They can move from atom to atom and atom to atom, and they keep going back and forth. An example of that would be looking like this, where the atoms are just floating around. This creates a couple of interesting things about metals. One, the reason why electricity can flow is the electricity are electrons that flow, and they flow through these already free electrons. This is why metals are electronegative. But also, the bonding between the metals is relatively strong because it's sharing so many electrons. And so if you hit the metal, it doesn't break apart because there are so many bonds, so many electrons being shared. They tend to hold together very, very tightly. And so the metallic bonding is really, really interesting. It's a different type of bonding. Now, when metals react, almost exclusively, they fall apart, lose electrons, and become cations. And that's how metals tend to react. But in a metal itself, the bonds between metal atoms have electrons that flow. Now, if I look at my wedding ring, okay, I have a 24 karat gold wedding ring. All right. Is this pure gold? No. It's the highest content of gold that you can buy in jewelry. Why is it the highest content of gold that you can buy in jewelry, 24 karat? Do you know why? Gold is super soft. If you had an absolutely pure gold ring, what would happen to it if you pressed on it? It would bend. Okay? And so rings and a lot of metals are what are called alloys. They are homogeneous mixtures, okay, or they are solutions of metals. Because if I look at my gold ring, it looks just gold, but there are other metals in there that I can't pick out, and so it is a solution of metals. There is also a solution of gases, like the gas that you're breathing in now, air. It's made up of primarily two gases, nitrogen and oxygen. You can't pick them out. You're bringing them in. It's a solution of gases. There are solutions of metals. There are solutions of liquids, but we usually think about solutions being liquids. But a mixture of metals that is homogeneous is called an alloy. And so they have properties of metal, but they contain more than one element. And an example would be stainless steel. It has iron with a little bit of carbon, 18% chromium and 1% nickel. It makes stainless steel, and it has a little bit different properties than just iron by itself. All right, overview time. This is a very important slide in terms of concepts for this chapter. Elements, okay? Most of them in the periodic table really you can't find. Okay, they don't exist as isolated atoms. Metals can. Okay, but to know you have an element when you write it on a piece of paper, it's this. It is written as the elemental symbol up there, and if it is written and there's nothing combined to it, and it has only one capital letter, it's considered an element, and you can identify it that way. So if I wrote the metal iron, the element iron, Fe, okay, I write that by itself, it is the element. A molecule, on the other hand, has two or more atoms bound together, and there are different ways in which you can bind those together. But traditionally, when you see a compound written, it looks like this. It is the symbols written together, bound together, and you will find at least two capital letters. Okay, two or more capital letters written. Now, it's very important. When you write elements, there is one capital letter and a lowercase letter. Do not rewrite those in any other way. If you write C and O for cobalt as capital C, capital O, that is a totally different thing. Okay, so make sure you write them the way that they're on the periodic table. Now, if you take a look at a molecule, okay, if you have a metal and a non-metal, then you know you're going to have a bond or a compound that is in the ionic region of ionic bonding. We call that an ionic compound. And if you run into a compound that has non-metals put together, then you're going to have a bond that is covalent, but a molecule that is called molecular. Okay, so that's important. Covalent bonds create molecular compounds. Now, molecular compounds, there are a couple things that we find. Diatomics are molecular compounds, and they have two of the same atoms. We know of 7 of those. Organics are important because you know that they are organic compounds. They have carbon with hydrogen and oxygen. Those are organic compounds. They're so important that we have an entire year of chemistry just related to organic compounds. And then acids are ones that are kind of weird. They can be fully nonmetals and nonmetals, but they kind of behave a little bit like ionic compounds. And so acids we're going to deal with specially. Okay, we're going to name them differently. They actually have a whole series of reactions that are important, and we deal with acids and bases quite extensively in GChem 2. So if I look at these 4 representations, how would you categorize this one? Is it metallic, ionic, covalent, or covalent molecular? Ionic, because potassium is a metal. All right, what would you call this one? It could be 2 things. Okay. Do I have a metal in this? No. They're all nonmetals. So that means it's covalent or molecular, but it's a very special covalent molecular one called an acid, because it starts off with hydrogen. What is this one? Metallic. What is this one? This is covalent. All right. Is this top one, number 1, is this a compound or an element? Compound. This one, is it compound or an element? Compound. This one, compound or element? Element. This one right here, compound or element? Why is that an element?
It's just one element, but it's two of that element.
And so we call that a what kind of element? A diatomic. There are 7 of those. What is the other element that has a subscript? Do you remember? Hydrogen is one of the diatomics. There is one that's not diatomic but has a subscript. Sulfur. What is its 8? Okay. All right. This is an oddball slide, but it's important. We can represent compounds in different ways, and the 2 ways that we can do that is in a molecular formula and an empirical formula. Okay? What is a molecular formula? It shows the actual numbers and the kinds of atoms. The empirical is the lowest whole number ratio. So you can say something like this. The empirical formula is like the lowest common denominator. Okay? Whereas the molecular formula tells you a lot more about the problem or about the compound. And so this C3H6 is a compound called propane, like propane gas that you grill with. It tells me I have 3 carbons and 6 hydrogens. Its empirical formula is CH2, the lowest common denominator. Both of those can be divided by 3. This right here, does anybody know what the name of that is? Hydrogen peroxide. It is a compound saying there's 2 hydrogens, 2 oxygens. Its empirical formula is HO. Now, if I gave you this, can you go to that? That's not too bad, right? So I'm not going to give you that. Later, in another chapter, I'm going to make you go this way. All right? But you need a whole lot more information. We'll do that later, not now. But I just need you to understand that we can represent molecules both in a molecular formula and an empirical formula, and sometimes it's necessary to do one or the other. All right. We're going to start naming, or we're going to start making some compounds, and then we'll name them. The ones that you can predict are ionic compounds, and so we're going to let you think about making some ionic compounds. Now remember, ionic compounds come from a metal and a nonmetal, and when they react, they form what are called lattices. I'll show that in a lot more detail at the end of the chapter. When I make an ionic compound, it has to be in its empirical formula, meaning the lowest reduced number. This is important because if you report it in a molecular formula, it's incorrect. We actually have to reduce these down. The formula comes from predicting the charge and then balancing that charge. Cations are written first, followed by the anions. All right, so what in the world are we going to do? All right, not enough steps here. Okay, let's write some things for you. So what you have to do to create an ionic compound: 1, predict the charge of each. Okay, so I have to predict the charge of each thing that's reacting. Okay. 2, you got to ask yourself, does 1 and 1 coming together balance? the charge. Because a compound should be neutral. When you have a compound formed, whatever comes together should be neutral at the end. Okay? If it doesn't, then you do the crisscross. Okay. For reduce, if you can. All right. That still doesn't make any sense completely until we do something. So let's attempt a few. Okay. Let's do magnesium with chlorine. Magnesium, if you look on the periodic table, what charge will magnesium become when it reacts? Positive 2. So Mg 2 plus. When chlorine reacts, what charge does it become? Cl minus what? Minus 1. All right. My first step. The two entities that are reacting, predict its charge. Okay. And for this one, I could use the periodic table to do that. Second step. I say, if I have a magnesium one of those and a chloride one of those, and I put them together, does that neutralize or balance the charge? No, it doesn't. And so I said then use crisscross. Now this is what crisscross means. I take the number value of 2 and I put it down there. And I take the number value of 1 and I put it down there. Now, I am a chemist. I am lazy. Am I ever going to write a 1? No. Because if I've taken the time to write magnesium, how many do I assume I have? 1. And then I would write the chlorine, and then what number do I put below? 2. Let me show you what that looks like. Magnesium with a plus and a plus. There it is. Chlorine with a minus. Chlorine with a minus. Balanced, balanced. Oh, look. They're the happiest place on earth. Okay? Everything is balanced. That's what I've done. Now, what I've done is I've balanced and done math with doing absolutely no math. Okay? Both sides have a negative 2 charge and a positive 2 charge. I've made the charges equal without doing any mathematics. Let me tell you, when I teach my non-majors courses, they love doing math with no math. Okay? And so they're very happy. All right. Aluminum with sulfur. What charge does aluminum become when it reacts? Plus 3. Because it has 13 electrons and it really wants to become 10. Sulfur, when it reacts, becomes a what charge? Minus 2. It has 16 but really wants to be 18. 1 and 1, do they pair up? They can pair up, but it's not balanced, right? So I use the crisscross. The compound, when it's balanced, will look like 2 and 3. All right. Lead. Ooh. Okay. It gave us some interesting information about lead. It said it's lost its valence electrons. All righty. In terms of lead, how many valence electrons does lead have? Be careful. Lead is number 82. What do we define as valence electrons? Only what? Only S and only P's. So how many S's past the last noble gas does lead have? It has 2 S's. The ones represented by 55 and 56. Now it has D and F electrons that are not part of the valence. But it also has number 81's electron and number 82's electron in the P. So it has 2 in the S, 2 in the P. It has 4 electrons. And so what this says is this lead reacts in such a way that it loses all of its valence electrons. What charge does it become? 4. Okay. That's one of the stable versions of leads, and it can become a +4. Nitrogen, when it reacts, what charge will it become? A what? Negative what? 3. The compound for this would be there. Lead has an alternative way that it can react. Lead can be a +2 also. And if it reacts with, let's say, oxygen, what charge does oxygen become? Minus what? -2. Do I do crisscross? No, because 1 and 1 coming together, balance. That's cool. Now let me complicate it up just a tiny bit. What if I asked you to react these two together? I told you lead can be a +4, and you told me oxygen becomes a -2. If I bring 1 and 1 together, does it balance? Doesn't balance 1 to 1. So what did I tell you to do? Do the what? Crisscross, right? What was the last rule I told you that we've never used? Can this be reduced? Yes. Now, could that be reduced? Could this one right here be reduced? How about this one? That can't be reduced. Can that one be reduced? Can this one be reduced? Most of the time they don't, but it's the one that's going to be on the exam that can be what? Reduced. Or CHEM-111 is going to do it to you, like every single time, just because it wants to. All right, perhaps one of you gentlemen would mind telling me just what outside the window that you find so attractive. All right, this cartoon has quite a good message in that we're in the South. Okay, now the ladies here are what? They are what charge? Positive. Ladies are positive, right? I got that. And the guys are what? Okay. And so we're in the South. Who goes first? The lady goes first. And when we write these, the lady always goes first. Okay? And so when we write compounds, cations, the positive ones, always go before the anions, the negative ones. Okay? And so if you reacted to things, okay, like oxygen and magnesium, what charge does oxygen become? -2. Magnesium is a +2. And if you put this down, OMG, it is wrong. Because why? They do react, but which one goes first? Yes, if you end up with OMG, you are wrong. All right, here is some of those. Crisscross actually shows you mathematically that the math will total to 0, okay, when you do these. All right, and so, all right, ionic compounds. When you do ionic compounds, Okay? You react lots and lots of different things. So let's react some things. Let's react, let's say, calcium, and let's do phosphate. Uh-oh. What's wrong here? What do you have to know if I write phosphate? You got to know that big sheet, right? Okay, all of them. So can anybody tell me what phosphate looks like? PO4. Okay, that is a phosphate ion, and it's an anion. Can anybody tell me what charge it is? -3. Okay, so even before I made compounds, I had to watch out here. Calcium. All right, this one is a little bit easier because calcium's on the periodic table. What charge does it become? 2+. Now, you can get to the point that you've memorized that, or you can look on the periodic table. The phosphate at this moment in time, the only way that you can tell what charge it is by memorization. Later, I'll actually make you calculate why that is -3, but that's a little bit too much at this moment in time. All right. To make the compound, what do I say? Does 1 and 1 balance? Nope. So what do? Crisscross. So I take the 2 and I take the 3, and I'm going to write Ca3PO42. Yes? By doing this, I have 3 calciums, right? I have 1 phosphate, and how many oxygens do I have? 42. That is not what I wanted, okay? Because this is what I really want. I want calcium as a 2+. I want 1 of those, calcium 2 of those, calcium 3 of those. And what I really want are PO4 3- and PO4 3-, so that I have -6 on the bottom, +6 on the top. But what I just wrote doesn't represent that, right? What did I forget? A parentheses. So I should have rewritten it like this. I said I need 2 of this group right here, PO4. Okay? Now, on the exam, what's going to happen? I will have one that has no parentheses. Okay? Just to be nice about it. Okay. Stop. Can't do it. Cyanide. Okay. Sodium cyanide. Ish. Okay, so what is the elemental symbol for sodium? Na. What's its charge? Plus. Cyanide. What is the group that creates cyanide? C and capital N. Okay, it is carbon and nitrogen put together. What charge does that ion have? Negative. And if I put those together, does it balance? Yes. Do you know what sodium cyanide is? Poison. Rat poison. Do you know what it smells like? It's the smell of almonds. So, sodium cyanide, not good to eat. Although, I wouldn't suggest eating much of anything in the lab. Okay, don't taste it. That's a lab safety guide. Don't taste anything. All right. What else? What can I do? Oh, Oh, we can do all sorts of things. Oh! Ammonium carbonate. Okay, ammonium carbonate. Uh-oh, now what do we have to do? I have to remember stuff. Wait a minute. To remember stuff, that means I had to actually look it up and learn it first. Okay, so we may even have to go all the way back there. All right, ammonium. Does anybody know what that group is? NH4. It has what charge? Positive 1. Carbonate. CO3. And its charge is a negative 2. If 1 and 1 come together, does it balance? No. Crisscross. Parentheses. I say this group, I have to have 2 of them. And carbonate, I have to have 1 of them.